Hello everybody, welcome back to my channel. Today we'll be seeing the significance of back EMF in DC motor. In the last video we saw the torque equation of DC motor. Today we'll be seeing this significance of back EMF in DC motor. Listen to me very carefully. I draw a simple diagram first. You can also draw this diagram. This will be IA, RA, EB, correct? And one symbol like this you can draw, and this is connected to the supply voltage V, and current is flowing like this. This is connected to the shaft which will rotate. Okay, mechanical output is given to the shaft that rotates as the motoring action takes place. This much you can write, this much diagram you can write, this much sentence you can write. Now three equations I want you to write. V equals to IARA plus EB, one equation done. Second equation, E equals to 5 PNZ by 60A. Second equation also done. Third equation, VIA is equals to I square A RA plus EB into IA, where VI is total power given to the motor. IA square RA is the power loss or the armature loss. EBIA is the gross mechanical output of the armature. You can tell like that. These three equations you have learned. After writing these three equations, I want to come to the main topic, the significance of back EMF. You should write this also. So now, what I want to do is first write this equation. E equals 5, EB equals 5 PNZ by 60A. From here we get EB is exactly proportional to N. EB equals to 5 PNZ by 60A. From this we got EB is exactly proportional to N. This is the first equation which we definitely want. Second is we want IE equation. So from there we get V equals to V equals to EB plus IARA. We wrote that equation before. So IARA is equals to V minus EB. IA equals to V minus EB by RA. From this we get second equation. IA is directly proportional to V minus EB. These two are the very most important concepts. In the previous one, we saw that torque is directly proportional to phi into I. This is not important here. I'm just telling you. I'll tell you one line that time you will understand. Okay. Just give me 1 second. Okay. So, okay. Now let's start. From this, there's two cases. One is full load condition. So when we suddenly add extra load on the shaft, the speed of the armature decreases. Use the words. When we suddenly add load on the shaft, the speed of the armature decreases. Because as the speed decreases, back EMF also decreases. As the back EMF from there we get that, from here we got that, as EB is exactly proportional to EB decreases. As IA is exactly proportional to V minus EB, as EB decreases, V minus EB will increase. Makes sense? EB will decrease, so the difference of V minus EB will increase. As V minus EB increases, the armature current increases. So more current is drawn to, it is drawn to satisfy the load condition. If the so that, what can we say? So the more torque is also required. More torque is used to satisfy the load condition. We can say here, because T is exactly proportional to phi. That's why I told you. Otherwise, you can just say more current is drawn to match the to satisfy the load condition. Second is no load condition. Here, when some load is suddenly removed from the shaft, the speed of the motor suddenly increases. Because speed increases, back EMF will increase. As the back EMF increases, V minus EB will decrease. As V minus EB decreases, IA will decrease. So armature current will withdraw less current to match the load, to satisfy the load condition. That's why we say that the DC motor is a self-regulating machine, because if more load is there, by itself will draw more current. Why? Because of back EMF. If less load is there, by itself it will take less current. Because why? Back EMF. So back EMF, because of back EMF, we can call the DC motor as a self-regulating machine. That was about it. Thank you for watching. See you in the next one. Bye bye.